So I'm Russ Cox, and I work on the Go compiler. And today the Go compiler is 80,000 lines of C code, and that's a big problem for us. One way to look at the problem is that programming in Go is fun, and programming in C is not. And I don't mean fun as in just fun, frivolity. Programming in Go is fun because it's a more productive language than C. There's great built-in support for CPU profiling and memory profiling. There's a garbage collector, so you don't have to track down self-inflicted memory corruption. There's good support for writing tests. There's good support for writing code coverage analysis. And all of this is missing from C, at least in the standard environments that we have to use for portability. And it makes writing the compiler more difficult than it needs to be. Another view of the problem is the one of expertise. Writing a Go compiler requires a certain amount of Go expertise because you have to understand Go in order to compile it. But then writing any program in C requires a certain amount of C expertise so that you don't plant a memory corruption bug that you have to track down 6 months later. And so writing the Go compiler in C means that the only people who can work on the compiler need expertise in both Go and C. And the Go constraint is fundamental, but the C constraint is not. And so the solution to both these problems, as you've probably guessed, is to write the Go compiler in Go. And so then the first obvious question after that is, why didn't we do this from the start? Well, at the start, Go didn't exist. And it's easier to write compilers in languages that do exist, although people have done it. And second, once Go did exist, it was unstable. We would change things when we realized that something was wrong. And it was much easier to make the changes when we didn't have to think about the dependency cycles caused by the compiler still needing to be able to compile itself. And then finally, an important point is that Go was intended for writing networked and distributed system software and not for compilers. And the programming languages are shaped by the examples you have in mind and you're building while you create the language. And avoiding the compiler meant that we could focus on the real target and not make decisions that would just make the compiler easier. Okay, well, given all that, why should we do it today? And well, Go exists, so that's good. That's why we're all here. With the Go 1.x releases, Go is stable. And although our initial focus was building servers, Go has turned out to be this very nice general-purpose language. And there's lots of big programs now. There's no danger that the compiler will be the only big program and will have this undue influence on the language design. Also, we're pretty much done with the language design, so that's another reason we're not worried about that. So now the question is, well, how do we convert it? And so one option is just to start over. And if you start over, there's several man-years of effort in the compiler. We don't want to repeat them. We don't want to not be able to do anything else for the next year or two. Another is to sit down with the compiler and translate it line by line by hand. And that would be tedious and time-consuming and error-prone. And so the option we've chosen instead is to make a program do that for us, to convert the C code to Go code automatically using a tool that we're writing. And once the tool is ready and the deployment story is worked out, we run the tool one day, and all the C code people working on turns into Go code, and from that day forward, we work on the Go version. And I should point out that that's not the end of the story, right? Just having it written in C code but in Go syntax is definitely not the end. Once it's written in Go, we can actually apply the profiler and see where it's spending its time, where is it spending its memory, clean it up and have actual package boundaries within it and all that sort of stuff. But that's not what I'm going to focus on today. And so the focus on today is just this conversion from C to Go. And if you remember the GoFix tool that we used when we did, before Go 1.x when we make API changes, this is sort of like one big Go fix. And so, this talk is about converting C to Go. And so the first thing I have to do is actually explain to you what C is, because not everyone in the audience actually knows C. And so I'm just going to review some of the details. So C started at Bell Labs in the early 1970s, and the first real big creative burst that produced what we would recognize as C today happened around 1972. And if you're interested in the history of C, Dennis Ritchie wrote this great paper called The Development of the C Language. Development of C Language at the History of Programming Language Conference in 1993. And in it, he wrote that C is quirky, flawed, and an enormous success. And then he went on to write, while accidents of history surely helped, it evidently satisfied a need for a system implementation language efficient enough to displace assembly, yet sufficiently abstract and fluent to describe algorithms and interactions in a wide variety of environments. That's the end of the quote. And it's exactly these quirks and flaws that make this conversion from C to Go interesting. So first of all, the data model. C was implemented on a PDP-11 with 24 kilobytes of memory. And in that context, every byte counted. And because the early users of C were coming from assembly, the programmer was placed very firmly in charge of the memory. And in that same paper, Dennis wrote that off-stack dynamically allocated storage is provided only by a library routine, and the burden of managing is placed on the programmer. If you've written C, you're used to having to remember when to call free and when not to call free. C is hostile to automatic garbage collection. And Go is the opposite. The language in the runtime is clearly in charge of memory. There's no pointer address arithmetic, and will free things for you. And then there's C types. These were a big advancement of C over its predecessors, but they're really only a convenience to the programmer. There was no intent to provide safety. They're for convenience. And unions are a good example of that, and we'll see unions in a little bit. And another interesting thing about the types is that C conflates this idea of a pointer to one element and a pointer to an array of elements. You use the same thing for both. And this was an important evolutionary step for C because it meant that a lot of existing code continued to work when that was introduced. But Go has two distinct concepts, pointers and slices. Another aspect of C is the control flow. Because C was one of the influences on Go, the control flow actually maps fairly directly. We don't have do-while loops, but they're easy enough to translate over. And then there's goto. And goto is actually the most significant difference, and we'll come back to that. Then there's the program model. In C, every file is compiled separately in a single pass. So there's forward and extern declarations, and there's separate shared header files. And when Go compiles whole packages at a time, and so all those concepts are gone. But most important, Go has no sharp define and no sharp include. And this is great for Go, but you have to address that when you're translating C code over that might use these. So that was C code in a nutshell, at least as much as it matters. So for the rest of the talk, I'm going to look at specific details of challenges that face a conversion from C to Go. I'm going to start with a few minor ones, unions, sharp defines, and comments. And then I'll talk about two bigger ones, gotos and type mapping. So our goal is automated conversion of our C code to Go. It's our C code, not all C code. And so we want the generated code to be maintainable. It's no good if it looks like it came out of a compiler. So it has to be at least as structured and clear as the current C code. And we want automatic translation to handle something like 99% of the code. More would be fine. But it's OK not to solve a general problem if there's only a tiny number of cases to handle. Special cases in the conversion tool are OK, and annotations in the source code to help the tool are also OK, as long as they're limited. So let's do some warm-ups. This is a union, or an example of a union, from the Go compiler. Val is the representation of a constant in the compiler. And for those unfamiliar with C, a union is like a struct in that it's got a list of fields. But in a union, all the fields sit on top of each other in memory. So it's only safe to use one of them. And you're the programmer are supposed to know which one to use. The union doesn't tell you. And so this example, there's a struct named val that contains two fields, C type, which is an integer, and then the union named u. And a code creating a val is supposed to set C type to record which part of the union it's using. And so if you're storing a floating point number in the val, you set u to, or C type to CT float, and then you set the fval element of the union. And then when you go to use it later, you're supposed to look at C type, see that it's CT float, and then know to read from fval. And if you read from some other field accidentally, that's fine. The program keeps executing, but it keeps executing with the wrong type of pointer, and probably you're going to have a bug or crash. And like I said before, the types are a convenience. They're not a safety mechanism. This is a good example of that. Here's another union. This one is in liblink, which is the object file generation library that we use in Go 1.3. And there's a struct named adder, has a type field and a union. And the details here are slightly different, but the big picture is exactly the same. So what do we do about these? Well, this is an old joke from the Plan 9 fortune file. And at the risk of killing the joke, the point is that turning all the structs into unions will in fact save a lot of space because you take the struct with many fields and you collapse them all into one place in memory. But then your program won't behave correctly if you're actually using more than one field in any particular struct. But there's a good idea here. If we flip this around and rewrite all the unions into structs, that's perfectly legal because you're only supposed to use one of the fields anyway. So if they're in different places in memory, you can't tell. And this is going to waste a little space, but it's a correct transformation. And so right now, maybe the experienced C programmers in the room are thinking, what about that idiom where you write to one union field and you read from a different one to interpret the bits differently? Like you write to an int 32 and you read from a float 32. And the answer is that's not valid C. The C standard says it's not valid C. GCC has optimizations that depend on that not being your program. And so as a result, if you write that code, it doesn't work today, and people don't do that anymore. So if you remember that, fine, but they don't do that anymore. And anyway, those are the only two unions in the whole program. So if I have to go in and rewrite them by hand, that's OK too. Next up is sharp define. So in a real C compiler, there's a preprocessor, and the preprocessor expands all the sharp define macros, and the parser and the compiler never actually see them. That's fine in a compiler, but in a translator where we want to preserve the actual semantic intent of the original code, we need to do something differently. And we had to handle them explicitly somehow. Luckily, there are not many sharp defines in our code. This comment says, you need super Gopher Guru privilege to add to this list. And this is actually from package runtime, but in the compiler, the situation is the same, even though there's not a comment saying it. And there really aren't that many macros. And some of them, like nellum and nil, it makes sense to teach the tool so it can actually do a good translation. So for example, nellum is really goes len, and nil is goes nil. And some other ones maybe are worth annotations. So what the converter does is it ignores all sharp defines by default. They're just blank lines as far as it can tell. But it will read the content of any comment that begins /*C to go. And so here in the first example, I've annotated the sharp define of bomb with an enum that's equivalent. And that's a real example from the code. I don't know why it's a sharp define. That was a mistake on our part. It should have been an enum from the beginning. So if there weren't a freeze, I would have changed this yesterday. But maybe others we should just rewrite. But again, there aren't actually that many, so it's OK. Next up is comments. This is a famous comment from the Unix 6 edition source code. I don't have to translate this program. But at the end of the comment, it says, you are not expected to understand this. And so if you're not expected to understand this code with the comment, you have no hope without the comment. So we have to preserve the comment somehow in order to write maintainable Go code. So how do we do that? Well, the approach in the translator is that we preserve the exact source locations in terms of the raw input byte number for all comments and all pieces of syntax. So we know where each comment is, and we know where each piece of syntax begins and ends. Names, larger expressions, statements, all syntax. And the lexer saves all the comments onto a separate list while it's going along, and the parser parses and never sees them. But then once the data structures are built, we go back through and we just sort the list of comments and sort the syntax. And we attach each big comment, the line comments, to the piece of syntax that follows them. So that big block comment in the previous slide would get attached to the if statement that was after it. And the line comment here that says keys and values make it to memory will get attached to the for loop after it. And the suffix comments, like until proven otherwise on the right-hand side, will get attached to the thing before it on the line. And so then now they're attached to the syntax. So any syntax transformations we do, and we can print it out, even if we move them to another file or something like that, the comments go with them. All right, go-tos. So C has a go-to statement, of course. And the text here is from Brian Kernighan's 1974 C tutorial, which we saw Hello World from yesterday. And he writes, C has a go-to statement and labels, so you can branch about the way you used to. But then he goes on to say, most of the time they're not needed. The code can almost always be more clearly expressed using for, while, if, else, and compound statements. And then there's more, actually. He says, one use of go-tos with some legitimacy is that you have a long loop and a while one might be too extended, which I assume he means indented. And then you might write the code with a go-to. And so another use is to implement a break out of more than one level of for or while, which we can do with explicit syntax now in Go. And then he adds, for the assembly programmers in the room, go-tos can only be used to branch to labels within the same function, which mattered to them. But thankfully, people have forgotten that might be something you want to do. And so this is the general spirit in which go-tos are still used in the C code that we have today. They're mainly being used to express specific things or very unusual control flow, but they're not being used just in place of standard syntax for the most part. So Go has a go-to as well, but we can't just translate C go-tos into Go go-tos directly because Go has additional restrictions beyond the fact that you can't jump between functions. In particular, we're trying to avoid the programmer ever seeing uninitialized memory. And so the first rule is that you can't jump over a variable declaration because the memory gets initialized at the declaration. And so in this example, there's an if x with a goto done, and that goto to done jumps over the declaration and use of y. And so that's not valid. It doesn't matter that the code after done never actually mentions y. The fact that y is in scope there means you can't jump over it. So the workaround is to bring the declaration of y up to the top of the function before the goto, and then it's valid. So that's an easy enough transformation to make if we need to. The second restriction is that you can't jump into a new scope. So basically, you can't jump inside a pair of curly braces that you're not already in. And so in this example, there's an if at the bottom that wants to go do the same cleanup as the if at the top, and so it has this goto bad. And that's not valid because the goto is jumping into the curly braces in the first example that it wasn't in at the point where the goto is. And so this actually doesn't have an easy rewrite. So another example of this is jumping between switch cases. And in switch cases, you can't see the curly braces, but each one of those cases is a different scope. So there's sort of implicit curly braces there. So we need a strategy for these kinds of gotos. And in this case, there's 3 different cases, and they all share some common code. So the interesting question is, well, how many of these are there? I looked recently, and there were 1,032 goto statements in the compiler, and they were jumping to 241 distinct labels. And so as long as we put our variable declarations at the top, and we're only jumping to labels that are in the topmost scope, so they're completely unindented on the page, those are all fine. So we really only care about the indented labels. Those are the ones that are going to be a problem to translate. How many of those are there? Well, there's 35 indented labels in the whole source tree. Of these, 18 are jumping between switch cases. 6 are implementing multi-level break and continue, which we can actually write now in Go. 5 are implementing the else half of an if-else statement, so there's not really an excuse for that. 4 are this kind of shared cleanup and return, like we saw in the if example. 1 is implementing a loop. It's a 5-line loop, so there's no excuse for that either. And 1 is, I cannot explain to you. It is none of the above, but the translator doesn't have to handle it. I can rewrite that 1. So to give you an example, here's a goto jumping between switch cases in the actual compiler. There's 3 different cases that want to be handled approximately the same. And so they all begin with some assignments that are the differences, and then they jump to this common code with the label common. So to translate this into Go, we can refactor this into 2 different switches. There's an outer one that groups all of the things with the common code, and the inner one re-switches and pulls out the specific pieces, and then the common code follows the inner switch. And so this is equivalent to the earlier one. It looks at r.op twice, so it's slightly less efficient. It's a little more repetitive, but it's valid and it works, and it's a reasonable transformation to do. It's still fairly clean. So that's the idea of what the translator would do. I want to point out that there's actually a very nice general solution to the problem of taking code written using nothing but gotos and inferring the high-level control flow. And I implemented this once for a different project, and it's really beautiful. It produces nice results, but it's completely unnecessary here. So the last thing I want to talk about is probably the biggest question, which is what Go type do you use for a particular C variable or expression or struct field? And this really isn't a trivial question because Go is a lot more specific about types than C is. For example, C allows implicit conversions between different integer types. And so C programs tend to be inconsistent about that because no one's really paying attention to it. And second, C doesn't distinguish between a pointer to an object and a pointer to an array. And in Go, you use a pointer for a pointer to an object, you use a slice for a pointer to an array. And so we need some way to infer, given a C expression, what Go type should we use? And I call this problem type mapping. And the way that we approach this in the compiler or in the converter is to build a graph of values that are flowing through the program as a result of assignments. And so, for example, if there's assignment x equals y, then x and y should probably be the same type in the Go program we generate. Similarly, there are some implicit assignments. So if you return x from f in the second block and you assign it to w, well, w and x should probably have the same type as well. Those are clearly related values. And then in the bottom block, the arguments to a particular argument in a function call probably all should have the same type, and furthermore, that type should match the parameter in the function. And so the 3 variables here, z, x, and y, should all have the same type. And so we apply this analysis to the entire compiler source. We pick up all the files, not just one at a time, and we build these sort of clusters of connected values. And in order to have reasonable clusters, you actually have to exclude some assignments. So for example, lots of things say x equals nil for different types of x. You don't want all of those x's to then be related because they're all assigned with nil. So nil has to be pulled out of the graph. And there's a couple other things like that you have to pull out of the graph. There's a function that writes an integer to an object file, and all the integer types end up getting called with that function. And so if you kept that function in, they would all get tied together. And you have to pull those out, but there's about a dozen. There's not that many. And then once you do that, you get these actually really nice semantically meaningful clusters. So let's look at some of those. This is a function in the C compiler. It's called isAllValue, or in the Go compiler written in C. It's called isAllValue. And it asks whether the expression represented by this node n, the piece of syntax n, can appear on the left-hand side of an assignment. Can you assign to it? And the various return statements end up contributing to one distinct cluster of related values. I don't expect you to read this. Here's the code without anything but return statements. And you can see that it's returning 0 or 1 or results from recursive calls. And then we also want to look at where that value goes. And so here's a little summary of the analysis. It says, well, the values were, this is the thing that gets returned from isAllValue. The actual things being returned or used are 0, 1, and then specific recursive calls. And then the context where this is used is always a Boolean. It's always if isAllValue or if not isAllValue. And so this is a great candidate for, you look at this, it's either 0 or 1. It's always used in an if. This is clearly a bool, right? And so in Go, the translation, this should be a bool. Here's another example. This is also from the compiler. It's called a function called checkSliceConst. And here it returns 0 or -1. And the only places it gets used is comparison with less than 0. So this is using a different convention, but a common one in C, where you return 0 on success and -1 on failure. And so this is another example where maybe the right answer here is a Go bool, where we tweak the constants. Or maybe it's a candidate for a Go error value, depending on exactly what, how much checkSliceConst reports. Here's another small cluster. This time it's a val, which we saw earlier. And there's two values in the cluster. There's this variable v, and then there's this expression varg, which is used when you're pulling things from ... in C. And the only places this gets used is with v arrow C type and v arrow u, extracting the fields of v. And so this is clearly just a pointer. There's no pointer arithmetic. It's just a pointer to one object. And the final one here is another small cluster. The values in this cluster have C type long star. There's a variable a1 that's initialized with this other expression. And it's used with the star operator and the plus operator. So this is pointer arithmetic. This should translate directly to a slice. The plus is you just do x equals x of 1, colon, and it moves along. Forward pointer arithmetic is really easy. Backwards pointer arithmetic is not as easy. But luckily, there is exactly one use of backwards pointer arithmetic in the compiler, and we can just rewrite that one. And so that'll be fine. So I've been showing you fairly small clusters because they fit on the slide. And most of the clusters identified by the translator are actually small. The median cluster size is only 4 values. But there are some big ones. The biggest cluster we have is almost 17,000 values. And it's all of the variables of type node star, which is the syntax for the compiler. And one really important point about this clustering is that it doesn't rely on C-type information at all. We didn't actually use the C-types to figure out that all the node stars were related or that this class of integers were related. And what this means is that you actually get these really interesting clusters that describe concepts in the program that weren't explicit in the C code. So for example, one of the big clusters contains all of the character constants and the lexical constants. And another one contains all of the variables and struct fields that hold sizes of objects or offsets into them. And so those are two different kinds of int. The first one might actually be rune, and the second one should probably be an int64 so that you can compile big values on 64-bit systems. And these can all be written using different specific types if we decide that that's worthwhile. And so that's really powerful. And the only place where I actually use the type information is a sanity check. If I get a cluster with 2 different pointer types in it, then I can print an error and say, something bad happened here. Maybe you should look at how these 2 different things managed to get connected. So a brief status report. We're still prototyping, but we can convert various fragments of the compiler to Go, and things really look pretty good. The main thing that's missing now is just the details of writing out the files, getting the imports correct, and that sort of stuff. But the big question was how to do this type mapping, and we figured that out. And we're aiming at doing this conversion for Go 1.4, but that's not a sure thing, but that's what we're aiming for. And on the topic of Go releases, everyone please try the Go 1.3 beta. because we need to find bugs and get them fixed for the release. And that's actually what we've been spending a lot of our time on, and we hope you all try it and report bugs for us. And so finally, that's how we're moving the Go compiler. And I hope I've convinced you that this is actually practical. This is a reasonable thing to do. It is actually something that the program can accomplish on its own. And I also think that it'd be really interesting to think about whether the same kind of approach, especially the value clustering, might be applicable to other C code bases, right? The fact that it was able to pull all these concepts out of the compiler that I didn't have to tell it about suggests that maybe other C code bases that maybe are important to you, you might be able to reuse some of this. Or maybe even code bases in other languages, right? The fact that it doesn't use type information at all means that maybe you can apply this to a strictly dynamically typed language. And maybe this is applicable, to writing program understanding tools that just help you with your Go code and point out, these are really kind of two different kinds of integers, except this one place, and maybe you screwed up here. And so that might be an interesting tool to build as well. So we've got some time for questions. Thank you. There's one there.
Hello, my name's Landon. Your talk was so good, I actually forgot at a period that I was actually in my pajamas still, so thank you very much. My quick question is, what can be done to help you guys get into 1.4?
I'm sorry, what can be done to help us get this in?
Yeah. You said you thought you could get there.
Right.
What can be done to help?
I don't know, file great bug reports. I think that's the main thing is, we really appreciate all of the bug reports that we get, especially the bug reports that have like concrete cases that don't work. That's by far the most useful thing we have. I call it Dave Cheney. Dave Cheney's been finding lots of Juju bugs, or bugs in Juju using the betas. And he realized that it was very complicated to get set up, so he actually set up a VM for us, so I could SSH in, see the bug, debug it, write the CL on my machine, and then, VM went away. And that was a great, here, this is how you reproduce. I know it's a pain, but just SSH into this. So reproducible cases are always the most important thing.
Yeah, have you found any?
Yes, and also once we do this, right, there's going to be a lot of work on making it real Go code instead of just Go syntax code. And there'll be lots of opportunity to help with that too. So watch the mailing list for that.
Have you found any bugs with this tool?
I have not found any bugs. I saw some code that scared me. But when I looked at it carefully, it was okay. There's some bugs where, or seeming bugs where there's variables in clusters in the multi-precision code that's both long, and long, and there are shifts, and at that point you worry because a long is 32 bits and long is 64, and are you going to sign extend wrong? But the words in question only ever contain 29-bit values, so it's all good.
Is there any expectations of performance parity or improvement when you do the translation?
I expect the performance initially will be slightly slower because there are bounds checks and things like that. But we've never been able to run a profiler on the C compiler, the C version of the compiler. And so the fact that we have memory profiling and CPU profiling, I think, means that we're going to be able to make it faster than it is today.
So a lot of communities have tried this in the past, Rust and Rabinius and such, and they end up actually not getting any more compiler contributions. Is that the point of this? And if so, is it Sisyphean?
No, so certainly I actually do think we will get compiler contributions because there are people who come up to me at the conference and said, how can I learn more about how the compiler works? I find it very hard to understand, right? And so part of it is converting to Go, and then the other part is making it like normal Go code. And so I actually think we will get more contributions, and I'm very happy about that. Even if we didn't get a single other contribution, for me personally, it would be worth it because I can use all the profilers, I have all these nice tools, I don't have to work on dangling point errors in C anymore. So I think it's going to be a big win for everyone else. But even if not, it's still a big win for me. Yeah.
Are you planning to apply this to some of the other C code that's in the Go source tree, like the runtime or the archaic C compilers?
I don't know. The C compiler is a big question because we have to translate the object generation stuff, and so it's not clear whether we're going to keep a C version and a Go version of that around, or if it's good enough and you can throw it at the C compiler, great. But it's not really a direct target. For the runtime, we do want to get all the C code off at least the Go execution, and that might be doing just stuff by hand. It's such a smaller amount of code that it might make sense to just do by hand. All right.